Hello friends. In the last video you have seen that we have to give check for internal stability, no tension failure, and the tension developed is the design tension must be equal to the horizontal pressure in the reinforced zone multiplied by the vertical spacing, and if it is geograde you divide it by CR. What is this CR? CR is the ratio of the geogrid contact with the soil, coverage ratio it is called. So it is called coverage ratio. If you are going to make use of strips, you might be covering lesser area. The whole area horizontally may not be covered, isn't it? Maybe 50%, 60%. But in geogrid, because the whole area is covered, but there are apertures. So coverage ratio is normally 0.8. So this is called design tension. The tension that is going to develop. Now, in continuation with further, friends, what should be the allowable tension? And what should be the relation between this allowable tension? This tension that is getting developed must not exceed your allowable tension. So this TD should be allowable tension divided by factor of safety. So factor of safety, we may write it like this, factor of safety. This factor of safety usually we keep it 1.5. And how will you find out this allowable tension? This allowable tension is called allowable tension divided by factor of safety. How will you find out this allowable tension? This will be the ultimate tensile strength divided by reduction factor for installation damage during the installation of the geosynthetic products. It may get damaged during installation. So you will have to give a reduction factor, which is usually 1.5 multiplied by reduction factor for creep. So RF for CR, also for chemical degradation and biological degradation. So reduction factor for biological degradation and reduction factor for chemical degradation. Right? So these are all factors that will give you this RF value. So RF means reduction factor. ID means installation damage. BD means biological degradation. CD means chemical degradation. CR means creep. So many. And how will you find out this ultimate tensile strength? In the specifications, the supplier will give you. But now you have got the universal testing machine for geosynthetic products, where you can carry out. So to find out the ultimate tensile strength of reinforcing element, that is geogrid here, we can carry out a test in the laboratory, tensile test or tension test. And the tension test, we call it wide width test. It is called perform wide width test. What is wide width test? You have a fixing jaws. Here you can place the geogrid, right? And there is going to be inside this particular this. So this will go. This is the fixing jaws, fixing plates, in which the whole geosynthetics, this is the geosynthetics. So your sample size in wide width test is going to be, this is 4 inch, this is 4 inch, that is 10 centimeter, and this is going to be 8 inches, that is 20 centimeter. And then you pull it, apply the tensile force, and deformation, you plot it here on the x-axis. What is the change in its width? Delta B. And the magnitude of the tensile force. So you will be getting the maximum tensile force. So you are going to get TU, the ultimate tensile strength. And then you can find out the allowable tensile strength of the material. So from the test, there is another test which is called narrow width. The sample size will be different. So these are the laboratory tests that you can perform it and you can find it out. And whatever tension is getting developed due to the horizontal forces must not exceed this. The tension that is getting developed must not exceed this allowable tension divided by a factor of safety. So this is very important, very, very important. So once I get the value of SV, how I can find it out? I have already seen that TD, the tension that is getting developed, is a function of tension developed, or design tension is a function of the horizontal pressure due to surcharge and overburden in the reinforcing zone, PHR, which I have computed just now. I have told you how to compute it, multiplied by the vertical spacing divided by coverage ratio. Therefore, what should be the vertical spacing? In internal checks, you will have to find out the vertical spacing. So vertical spacing is going to be TD multiplied by CR divided by the horizontal force that is getting developed. So what is the horizontal force that is getting developed in the reinforced zone? You have seen it. It is going to be the coefficient of active earth pressure in the reinforced zone. This zone up to here is the reinforced zone. This is non-reinforced zone. So, depending upon the value of phi r, Kr will be calculated, coefficient of active earth pressure, multiplied by gamma r into z at any distance, at any vertical distance, z at any depth, and due to surcharge, Qs, you can calculate it. And therefore, this vertical spacing SV is going to be tension that is getting developed into CR divided by KAR into gamma R into Z plus QS. So this is known to you. This should be allowable tension divided by a factor of safety. And how the allowable tension is to be calculated? Depending upon the ultimate strength, you can carry out the test, or you know the values, divided by the factor of safety for uncertainty, installation damage, creep, biological degradation, chemical degradation. So this is known. This is known. Therefore, this is known. So this is known. Coverage ratio normally is 0.8. It will be, you can find it out, the coverage ratio, depending upon the holes. So this is known. This is called coverage ratio. Coverage ratio. This is known. because you know how to calculate it. 1 minus sine phi r divided by 1 plus sine phi r. This is known. This is the property. Unit weight Z plus surcharge is known to you. So you get this equation 3b in terms of Z. So the equation 3b is obtained in terms of Z. So let's say I want a vertical spacing of 0.5 meter. What would be Z maximum? That I can calculate for, says, SB equal to 0.5 meter. Vertical spacing I want to provide at every 0.5 meter. What should be Z max? I can find it out. Say for 1 meter spacing, what should be Z maximum? Up to what depth I can provide so that there is no tension failure. You got the point? So vertical spacing can be calculated without any problem. And up to that depth, let's say for 1 meter you get it up to maximum depth is 3 meter and the wall is 7 meter or 8 meter. So up to 3 meter from the top, you can provide the vertical spacing of 1 meter. But as you go down, the vertical spacing, you will have to provide it 0.5 meter. When I take a design problem, I will elaborate it in detail. So one part is I can calculate this. So there is no, I have calculated this. Now, the question is how to find out the effective length. What is the effective length? As I told you, this is the slip surface, and beyond, from slip surface up to the end, this is called the length LE, and this side is called LR. So how will you find out LE? That will come from pull-out resistance. So to find out the length of the reinforcing layer, friends, I know that I have to calculate LE and LR. Now this angle is 45 plus phi by 2, phi r by 2. Therefore, with the vertical, this angle will be 45 minus phi r by 2. So if I take, this is the Z. So at any depth Z, the remaining length is going to be h minus Z. So at any depth, Z tan of 45 minus phi r by 2, this angle will be the opposite side here. What is that? It is going to be how much? H minus Z. So it is going to be this distance, that is going to be LR at a particular depth Z. So at a particular depth z, LR, opposite side, this is LR. At depth z, divided by this side, that is h minus z. Therefore, LR at any depth z will be h minus z into tan 45 minus phi r by 2. So LR is known. Now friends, you can find out from pull-out resistance the LE value. This LE at any depth z can be found out from here up to here. It is called LE at any depth z. How will you find it out? So you will have to find out from calculating the frictional resistance or pull-out resistance against pull-out. Frictional resistance. As I told you, the very assumption in the analysis and design is that the friction is to be calculated for the reinforcing length outside the slip surface. So outside the slip surface at any depth z, I know what is the length. It is going to be LE z. Now, what is the vertical pressure here on this? So I can find out the vertical pressure at z due to the fill material and also due to surcharge. The vertical pressure can be calculated, multiplied by tan delta will be the horizontal pressure. So vertical pressure, there is the reinforcing element and there is the vertical pressure. Sigma V at Z multiplied by tan delta will be the horizontal pressure multiplied by LE. It is acting here as well as here. So 2 times multiplied by the interaction coefficient multiplied by the coverage ratio multiplied by LEZ. So 2 times, friends, it is going to be, remember it, 2 times CI, CR, LE, sigma V at any depth Z into tan delta. This is the pull-out resistance. This is the pull-out resistance. And this pull-out resistance, PR, must be equal to the horizontal force that is getting developed due to the in the reinforcing zone due to overburden as well as due to surcharge multiplied by SV multiplied by this CR, coverage ratio. Friends, this is very important that there is no multiplied by factor of safety. Multiplied by factor of safety. Therefore, friends, it is going to be TA equal to TA. the tension that is going to be developed. So allowable tension and the frictional resistance, if you are going to equate it, this tension that is developed should be less than equal to the frictional resistance, always. So if you equate it, therefore, equating TD equal to this frictional resistance, we get 2 times Ci interaction coefficient. This is called interaction coefficient, normally 0.75, into coverage ratio into Le into sigma V tan delta must be equal to this, equal to what is the tension that is getting developed is PHR into SV into factor of safety 1.5. Now PHR is a function of Z. As Z increases due to overburden, the pressure is going to increase. So at different depth, therefore, you can find out the value of Le. You know Ci, you know Cr, 0.8, 0.75. Vertical pressure is going to be due to overburden, gamma into Z. Delta is angle of wall friction, that you can find out. From the pull-out test, you can perform pull-out test and find out the value of angle of wall friction between this material, fill material, wall fill material, and the reinforcing element. Therefore, delta is known. Or you can assume it depending upon the texture, roughness of the reinforcing element. Delta could be at the max, it could be phi, r, or the lesser value will be 2/3 of phi. So what is the length required at different depth can be found out. Therefore, friends, you already know LR. Now, therefore, you know Le. So, Le can be found out. So, friends, it will be PHR, which is a function of Z, into SV, into factor of safety. SV is already known to you. Factor of safety is already, this is in terms of Z, divided by 2 times Ci, Cr, sigma V, the vertical pressure, into tan delta. So at different Z values, what is the length Le required? So as you go from the top, Z is going to increase up to the bottommost part. And you can find out the Le. LR you have already calculated. And Le also you have calculated from this equation. Therefore, the total length of reinforcing layer or reinforcement is going to be Le plus LR. Everything is known to you. So with this, you have completed the internal checks based on pull-out resistance, based on tension developed, what is the vertical spacing, what is the length of the total length of the reinforcement. Everything is known to you. So friends, I know therefore SV, I know the length of the the vertical spacing as well as the length. This is called internal stability or internal checks. Now, we have to give the external checks. We have to go for external checks. So, quickly I will cover that. Otherwise, the number of videos will increase. So, I will give for external checks. So, checks for external stability of the wall. So, first check is for sliding. So, for sliding, if this is the wall, right? With the wall. With the wall. Sliding. Calculate this. The horizontal pressure due to backfill. So there is the backfill. What is the properties of the backfill? Backfill soil. The property is phi b is the angle of internal friction of the backfill B. Then what else? Gamma B is the total unit weight. Of the backfill. And the active earth pressure for the backfill, you know it. Therefore, due to overburden, what will be the pressure distribution? Friends, if you draw the pressure distribution, it is going to be quite simpler. You know it. So the pressure distribution is going to be like this. At any depth Z, what will be this in the backfill? Ka for the backfill into total unit weight of the backfill multiplied by Z. There is the horizontal pressure in the backfill, isn't it? And if there is surcharge, there is the pressure. So you can find out the total horizontal force PH will be PA, which is coming from the backfill, is going to be KAB into gamma B Z plus this due to this, it will be half KAB gamma B into H square, the total height, plus this will be KA of backfill into QS. This is due to surcharge on the backfill. So this will be KAB QS multiplied by H. This will be acting at H by 2, and this will be acting at H by 3, triangular. So, if you want to have for sliding, factor of safety for sliding, what is the resisting force? Resisting force will come due to the weight of this reinforcing zone. What is the weight? Length is already known to you. Height is already known to you. Gamma is already known to you. So what will be the weight? WR will be the unit weight, gamma R for the reinforcing zone in kilonewton per cubic meter, multiplied by the length, multiplied by the height per meter. You get the kilonewton per meter length of the wall perpendicular to this. L into H. This WR will resist this sliding force. This is the sliding force, horizontal force. This is the acting. And this is going to resist. So what will be the resisting force developed here? The resisting force FR will be WR into tan delta at the base. At the base, what is the at the base? What is the delta? That is, therefore, the factor of safety is the resisting force which you have calculated divided by pH, the force, pH, horizontal force, and this should be greater than or equal to 1.5. What is the next check? Overturning. So give another checks. This is the first check. The another checks is for overturning. These are all simple, which you have learnt earlier also. So how to give checks against overturning. Overturning, OT. So factor of safety against overturning will be, this will try to overturn it. So you can find out the resisting moment, this weight will try to resist it. About this point, if you take the moment, the resisting moment divided by overturning moment. And what is the resisting moment? It is the WR, and this is going to be L by 2. So WR into L by 2. Right? And what is the overturning moment? This is going to be half KAB gamma B H square. So half KAB gamma B H square due to overburden multiplied by H by 3 plus the another force KAB QS into H. This is the force which will be acting at H by 2. So you know MR, you know MR. Everything is known to you. And therefore, factor of safety you can calculate this should be greater than equal to 2. And the third check is against bearing capacity failure. So this is also very simple overturning, bearing capacity failure. You have to find out the eccentricity E, and you know the famous formula for eccentricity. All of you know it, MO divided by W plus QS into L. So E should be less than or equal to L by 6, where L is the length of the RE wall. And E is calculated very simply from the expression MO, that is the overturning moment, divided by under bracket W, that is the weight of the reinforcement, that is the wall, plus QS, that is the surcharge acting into L. And then you can find out the effective length. L will be total length minus 2 times E. And once you get this, you can find out the bearing pressure. So bearing pressure can be found out. What will be the bearing pressure? It is very simple. You already know gamma R. You know the height. So what is the height? Into 1 plus QS, the surcharge, if there is any surcharge, right? Multiplied by L multiplied by L divided by L prime. That is the bearing pressure. And what is the safe bearing capacity? From any formula, Meyerhoff, basic, IS code formula, Tarjag is bearing capacity, Q safe. You can find it out for this. So you know the value of Q safe. So safe bearing capacity is known to you, and therefore the factor of safety against bearing capacity failure, factor of safety against bearing capacity failure will be Q safe divided by bearing pressure. This should be greater than equal to 3. Friends, with this, the complete analysis and design of RE wall, geogrid reinforced earth wall, is complete. Thank you very much.